Okay, welcome back everybody. This is our Friday lecture, third of the week, third virtual online lecture on Wells hydraulics. A couple updates. I am working on getting the sound better. Hopefully that works a little better this time, and I'm waiting for a gizmo on Sunday, so hopefully we'll have better sound next week. Okay, so on the menu for the day, we will do the steady state unconfined aquifer case, so very similar to last lecture, but now with the unconfined issues. And the main course for the day is the transient confined flow, so what's called the Theis method. So we'll go back to the general form of the flow equation with the time varying head. And see how we can perform finally well tests, like realistic, I guess, well tests, real life aquifer tests with a well, using the time evolution of the drawdown in the well. Okay, so just a quick reminder of last lecture. We used confined aquifer, and starting with a mass balance or a water balance, I guess, the continuity of discharge, across those cylinders away from a well, with two observation wells at distances R1 and R2, with head in there of H2 and H1, then we could calculate transmissivity. So today is very similar, but now we're going back to the problem of unconfined aquifer, meaning the water table actually moves, right, as opposed to a confined aquifer where the depth of the aquifer is always constant. So we have that B that's a constant, and we don't have to worry about it. Again, we've seen these issues in chapter 4 over and over, so hopefully that is now becoming easy for everybody, right? So if this is H0 here, in an unconfined aquifer, the water level actually drops, right? The water table actually drops. And now H is a function of R, of distance, so we have to plug it into our equations. Okay, so same slide as before, but now for the unconfined case, right? So last time we did the confined, this is the unconfined, and here on the top right, you notice I have a little bit of eye candy. So if you want to look at this while I talk, this is in Yucatan, Mexico. This is a karst formation, so those Swiss cheese sort of underground caves, and you can call this a natural well. Okay, so going back to what we did last time, right? Discharge is the Darcy flux times the area. Again, I spent the time last time explaining this area. So this is the sleeve, this is the cylinder, away from the well, the outside area of that. So we have, again, our circle, right? The perimeter of the circle up top, so 2 pi r. Again, notice h here instead of b, right? Because depending on how far we are, h is actually a function of the distance, so it's not a constant. And of course the Darcy flux here is the same, so it's K times the AHDR. Okay, so now we separate our variables like we did before, but now again, notice how H shows up on the left, and of course B has disappeared from the right. Everything else basically is the same. Again, because B has disappeared, now we're left with hydraulic conductivity and no transmissivity, obviously. Now when we integrate those two things, right, same as before, integrate from 1 to 2, and integrate from 1 to 2. So you can see on the right here we'll get the same thing, right? The natural log of R2 and R1. But on the left here now we have to integrate H. So the integral of HDH is going to be H squared over 2. Now H squared over 2, right? So this divided by 2 on the left hand side from the integral. If we flip it on this side, right, we end up with 2 over 2, and the 2's disappear. So this is basically, again, h squared over 2 is the integral, right? So what I'm saying is if I flip this 2 on this side, you can see how these cancel out, and now they're gone. Okay, so all that said, now we end up with this equation here on the bottom left, with now the squares on the left-hand side, k instead of t on the bottom here, and the 2 has disappeared. Otherwise, very similar expression. Now, typically what we are looking for is k, and we measure H2 and H1 at some distance R2 and R1 in 2 observation wells, and now we have a complete equation by which we can calculate k. A quick problem example. So this is the exact same problem as you did home, last lecture for attendance, but now we're in an unconfined aquifer. Also, I realized that I forgot to change the wording. So on your take home last time for last lecture, you should have said confined, not unconfined, obviously, and then you should have said depth to the water. So in this case, for the unconfined case, it's actually depth to the water. But for the confined case, it should have been depth to the piezometric surface, right? But anyways, otherwise, everything's the same, right? 500 liters per minute, 5 meters and 2 meters in the first and second well that are 8 and 3 meters away. And then the aquifer depth is 10 meters. So everything is the same setup. Now, when we calculate this again, now we have K equals Q over pi, Q over pi h squared differences, right? And natural log of the distances. Okay, so 2, 1 are the distances, 2, 1 are the distances. Okay. Now we do some conversion, right? So we have, I'm getting lost here, 500 liters per minute. So you convert that to cubic meters per day. It's always better to work in meters and days, right? So now we have 60 times 24 minutes in a day. And then those liters, which convert them to cubic meters, so 1,000 liter per cubic meter, right? And that gives us the discharge in cubic meters per day. Now we have our natural log of the distances. So these are, what was it, 8 and 3. Okay, and then here on the bottom we have pi. And then we have the h. So the h, just a note for those of you who didn't see it again, h is the difference between the stable surface minus the water depth, right? So it's 10 minus 2 and 10 minus 5. So 10 minus 2 is 8 squared minus 10 minus 5 is 5 squared. And this is it. And now we plug all that in a calculator or MATLAB in my case, and I find, and sorry about that, I keep doing this, 5.8 meters per day. Again, compare that for the unconfined aquifer to what we found for the confined case, which was 3.7, I believe. Right? So again, for exactly the same pumping rate, exactly everything, exactly the same, right? You see that we need more hydraulic conductivity in the formation for the unconfined case than the confined case. Okay. All right. Now, moving on, just a last quick note on those steady state cases for confined and unconfined. And again, Jacob's well here in Central Texas, the same thing as the Yucatan well. This is basically a karst, so a Swiss cheese formation, where you can actually see here. You can actually see the water table or the surface of the aquifer, right on the surface of the soil here. So that's kind of cool. Okay, so another thing we do with those steady state equations that we can do for the steady state equations is to find the drawdown in the well or the radius of influence. And I'll start with this definition of radius of influence. The radius of influence is basically the distance at which your well is not influencing the water table or piezometric surface anymore. And obviously you can see how this is important, because let's say you want to put another well somewhere, you probably want to be at 2, for the same pumping, obviously you want to be at, at least 2 radius of influence. So you can put another one here, right? That would have something like this. right? If you're closer, then you're going to need more gasoline, more electricity to pump the same amount, because now you have this other well interacting with yours. That's a problem, right? So you can see if you have a well here, right? This guy is doing this, and now, you know, here you have, oh my goodness, here you have a problem with interaction of the two wells. Now, the way you find the radius of influence, and I'm sorry, you know, something is sensitive here. Excuse me. Now, the way you find this radius of influence is typically you replace, and if you do it with the confined equation, it's a little bit easier maybe to see. Right? So you can see that, let's say H1 now is the drawdown in the well, right? So you have the drawdown in the well, S, which is equals to, you know, this whole equation, and then H2 is the stable level, which you would know, right? Because you know, before you start pumping, you know what the water level is in the well, so that would be your H0. Now, as you start pumping, right, and when you reach that steady state, now you know what that water level is, so you know what that drawdown is. Now, so you know this, you know, number on the left. If you know your well casing, you know, the size of the radius of your well, basically this little circle here. Now the only unknown left, right, is R2. So you can calculate R2 as the distance at which, you know, the head is actually H0. So that's a way you can calculate your radius of influence and know how far your well is influencing your water table. Okay. Now that was just a quick note on, you know, radius of influence. We'll do a couple of example problems on this later. But I want to get to the entry of this lecture, which is the Theis method. Okay, so now we're going back to transient equation, right? So remember, this is the whole flow equation, basically when, you know, head is allowed to change over time. One advantage is that now the storativity also shows up, right, if you remember those equations. So we'll be able to calculate the storativity of the aquifer, which obviously, when this whole term is 0 here, we cannot do, right? We only had the transmissivity that we could measure. Another reason to use these pumping tests are the stable state or the steady state is usually takes a long time, right? It can take days to reach the steady state, and then you need those, you know, observation wells. So again, here we'll use to start with, we'll use an observation well away from the pumping well. But in some cases, and we'll discuss them later, we can do slug tests. So we can literally use just the one well and look at the drawdown in the well, in the actual pumping well. And we can actually get all the aquifer parameters just from the one well, which obviously we want to do because, you know, drilling wells, if you remember from the first lecture on wells, those drilling rigs, right, when you drill a well, it's really expensive, basically, right? They charge you by the foot, and it takes, you know, specialized equipment. So obviously when you do a well, you don't want to drill 2 holes just to have, you know, the numbers, right? You want to drill 1 hole and 1 hole only. So we'll see how that works. Again, for today, for the Theis method, we still have an observation well that we need to use. Again, just a quick reminder, so the linearized boostiness equation, or, you know, general sort of flow equation here. So for a confined aquifer with no leak, not a leaky confined, but just a regular confined, right? There is no recharge to speak of, right? There's no leakage from anywhere, from any other aquifer. So we end up with this equation, and note that I replaced the head with the drawdown, which is basically the same, right? Again, these 2 equations are equivalent because the drawdown is just a mirror image of the head. Now note, this is much easier to get, right? Because this is just the depth to the water surface, so we don't need to know the depth of the aquifer itself. Okay, so we'll work with this equation here. Again, just a quick reminder of the assumptions, you know, same as before. We have a constant horizontal aquifer that is confined. You have a constant pumping rate, and now we're looking at the drawdown, which is the H0 minus H at some point away. Okay, so here is the gist of the method, or the important part of the method. Now, if you remember from the steady state equation for a confined well, right, that's the simple equation we had before. Now for the unsteady, for the transient solution, and again, I'm not working out those numbers for you. There's a bit more detail in the book, in chapter 5, if you would like to see how this is derived. But what's important here is the similarities, I guess, between those two equations, right? So on the left-hand side, we have the drawdown. Here, the drawdown, like the difference between two heads. Here is just a drawdown at one point. Again, Q over 4 pi t, Q over 2 pi t, right? I won't discuss where that comes from, it doesn't matter. But you can see this is a constant and similar equation. And now the important or the interesting new part is the WU. Okay. So what you want to remember here is that U is time, right? So U, here you have the expression for U. So again, WU is what we call the well function. Okay. So the well function is plotted as the Theis curve for the guy who did it first, I guess. Now, what's important again is that the well function is a function of time, right? So U is a surrogate for time. You can see time is here, and then that's because we're, again, in a transient flow equation, so there is time in there, right? Now, notice that the well function itself, WU, is plotted as a function of 1 over U, not U, 1 over U. Notice 1 over U is literally time, right? It's some constant, storativity, transmissivity, wherever that radius is, that observation well is, but 1 over U is basically constant times time, so it's just time, right? So basically, WU is the expression of drawdown over time, right? So if you look here, again, the equation drawdown on the left-hand side is some kind of constant times the well function. So again, here, this is drawdown, basically, right? Transform drawdown, if you want, constant times the drawdown. So this is the drawdown. And here, this is transform time, right? So drawdown versus time, well function versus 1 over U. This is what we're looking at. So meaning if we actually look at drawdown in a well over time, we should expect it to look like this. That's the whole point of this curve, and which I'll show you in a minute, okay? So drawdown versus time should look like the well function. Now, if we look at real data, and again, this is from your book, so you can go back and look at those. This is actual drawdown data, right? Drawdown versus time. Oh, another thing I didn't mention, but this is in log, right? So this is important. This is log, right? Log scale, okay? So you plot your data. So literally what you do is you start pumping, right? At some time, 0. And then you look at the drawdown over time. You take the numbers, right? This is where my water table is, or piezometric surface. This is where the water is, so on and so forth. So you take data over time and you plot it in log plot. And you can see that they look similar to the well function, right? Which is kind of the principle of this method. Now next, once you have that plotted in log, what you do, you overlay the two, right? So the old method, the graphic method, would be to literally take those two, plot your data in a transparent sheet, right? And then line it up with the well function. Once they're lined up, you're locked in, so you stop. What you do now is you take what we call the match point. Now typically the easiest thing to do is to take that match point at 1 and 1 on the Wells function. So that would mean 1 over U is 1. If 1 over U is 1, when 1 over U is 1 here, right, it's really easy because U is 1, so you can plug 1 into your equations. And then same thing when WU is 1 here, right? When you go here, right, you'll plug 1 here and you'll plug 1 here. It's going to make everything super easy. So just take your match point as 1 and 1 on the Wells function. Once you have that match point, go look at the value of your time and your drawdown on your data, right? So here you can see that the match point is right above that second point here. So right above, So match point here, right above the second point, so here. Let me try and go somewhat straight with my system here. Okay, and then on the y-axis, it's right aligned with that fourth point here, so it's right here. Right, so this is the match point that we had. And now we can go on the axis and read here, and then right, and then down. Well, that's not very straight, but here. Okay, so you can see here again. Remember, this is in log scale. So this is around 2 somewhere, and this is actually around 4 somewhere. In reality, this is in the book, and obviously, if you had the actual plot here, you could use a ruler and be a little more precise. In the book, they say 4.1. Now the 0.1, you can spare it, but this is actually 2.4, right? So if you were kind of guesstimating or reading it with a ruler, you could probably guess 2.5 feet and then 4 minutes, right? Okay, so now that you have read the drawdown in time from the data corresponding to your match point, right? So now again, remember we have WU is 1, U is 1, drawdown is 2.4, so little s is 2.4 feet, and then time is 4.1 minute. So now we have everything we need, so then the last step is obviously use your equations, start with the transmissivity. The reason we start with the transmissivity is because we need it then to calculate the storativity, right? So the transmissivity, we have everything. This is 1, this is the drawdown, Q is known, obviously this is the pumping rate of your well, so you can see we can plug this and that in and calculate transmissivity. Once we have transmissivity, we can plug it in here. Now we have transmissivity, U is 1, time we read, right, 4.1 minute, and then R is again the distance of the observation well, so we know that as well. So we can plug everything in and calculate S. And this is the whole Theis method, right, 1, 2, 3, 4. Now an example, again, same example, but just actually solving it. I already explained the match point and how we got S and T over there, S and T. Right, so now that was from basically this point here and this point here, that's your S and T, so you read that from the graph. And then finally we can calculate T equals, right, T equals Q over 4 pi S WU, W of U. Right, so Q equals, so I transform the 220 gallons a minute corresponds to 42,400 cubic feet. So I left everything in, again, American units here, but I do it per day. Right? So again, this is the conversion for Q, then 4 pi, and then S is the one we read, so 2.4 feet, right? So again, you see that I'm using everything in standard, and then times WU, which is 1, and again, you see how that this is convenient to use 1 and 1 as the match point, because now you have 1 and you don't have to worry about double guessing here. And if you solve this, you get 1,400 square feet per day. Now you have that, you go into your storativity equation for pi tt. What is that? Oh, sorry, k first, of course, since we're asking t and k. So k is t over b, right? So nothing new here, very simple. And that would be 29 feet per day. And you can see that this is coherent with what we've seen before, meters per day. Okay, so here, here, and then finally S equals 4 TTU over R squared, and now you see how everything is lined up and appears, right? So we know T, 1400, we know little t, 4.1 minutes, we'll have to convert that again, so 4.1 minutes is 4.1 divided by 60 times 24 minutes per day, and that gives you 2.9 E minus 3 days. So again, 4 times 1400, these are square feet per day, times 2.9 E minus 3, 10 to the minus 3 days, that's your time, divided by R squared, so 824 feet squared. And then again times U, but U is 1, right? So times 1, So that's the convenience of that. And then you end up with 2.4 E minus 5. And remember, storativity is in percent, right? You need less, basically. Again, remember from the previous chapter, chapter 3 and 4, that the storativity for an unconfined aquifer would be basically the specific yield, right? So near the porosity almost, right? Minus the retention water. But for the confined aquifers, storativity is linked to the compressibility of the material and water, so it's much less, right? So those numbers make sense, basically. So this is it. This is how you use the Theis method. Again, you start with plotting your data on a log, then you match it, you take the one point, you read on your data what that corresponds to in time and drawdown, and then you use your equation to plug it in. I will leave you with this. I'll give an example to do at home, and then on Monday we will continue on the topic of Wells hydraulics. Thank you.